Welcome back, dear students. So from today's class onwards, we are going to discuss on design for flexure of a pre-stressed concrete member. That is, we will see for the check for permissible stresses at transfer as well as at service. That is, we have a flexural member. There arises two critical situations, and that is, first one, at the time of transfer. The pre-stressing force and the minimum service load will be acting. So the section should be safe in that pre-stressing force which is maximum at the time of pre-stressing, and that is at the time of transfer, and there will be minimum service loads. So that is the first condition. And the second condition, obviously, at the time of serviceability or at the time of limit state or at the time of service, there will be the minimum pre-stressing force. Minimum pre-stressing force in the sense the pre-stressing force after all the losses and the maximum service loads, that is the service load which will be acting at the service time of the building. So if I am seeing these two situations, the concrete or the member should be safe in taking all the stresses. Okay, so if I am having a beam cross section like this, having a pre-stressed tendons, then due to the direct stress or the pre-stressing force, there is a direct compressive stress, that is P by A, and the eccentricity will create, this is the eccentricity, will create a bending stress which makes tension at the top and compression at the bottom, and you will get P by A, the compressive stress, direct compressive stress, and the bending stress P into E into Y by I at the bottom, and P into E into Y by I at the top, which is tensile in nature, and the bottom which is compressive in nature. And together, these two together we call it as F inferior, that is the stress, inferior stress. We have discussed that before in the lectures. And this together we call it as F superior, that is the stress at the superior fibers, and this is the stress at the inferior fibers due to the pre-stressing force. And after losses, you can see after losses, for these two after losses, that is percentage of loss into P by A minus P into E into Y by A at the top, and similarly at the bottom you can get it like this. And at the service condition, or due to the live load, you will get a bending stress distribution like this, that is at the top you will get compression, at the bottom you will get tension. Similarly, you will get due to dead load moment, you will get bending stress variation like this. This we have discussed in detail. Now I will combine these two, that is the stresses at transfer. I could write it as at top fiber, that is at top fiber due to transfer, and the stresses at transfer time there is no losses, that is you have P by A minus P into E into Y by I plus MD into Y by I. That is, you can see here at the top fiber at the time of transfer, P by A minus P into Y by I plus MD into Y by I. This must be greater than or equal to FTT, where FTT is the permissible stress in tension at the time of transfer. So this is the permissible stress in tension at the time of transfer. Now at the bottom fiber, it should be P by A plus P into E into Y by I minus MD into Y by I, and it must be less than or equal to FCT, that is the permissible stress in compression at the time of transfer. Similarly, at working load, you have working condition, you have after all the losses, that is you have the efficiency factor into P by A, that is loss factor into P by A minus P into E into Y by I plus MD into Y by I, and here there comes the dead live load moment also, and this must be less than FCW. Now if you see the stresses at transfer, that is you have the transfer state, you have the condition like this. At the top it is tension, and at the bottom we have compression due to the pre-stressing force. So at the top fiber it should be P by A minus P into E into Y by I plus due to dead load moment MD into Y by I, and this load should be greater than, this stress should be greater than the tensile stress, that is the allowable tensile stress in tension at transfer, that is FTT. And similarly at the bottom you are having compression, that is the bottom fiber. The permissible the value for your bottom fiber stress should be less than or equal to FCT in, that is the permissible stress in compression at the time of transfer. And similarly at the working time you have, at the working load you have the profile like this, that is you have most probably you have the compression at the top and tension at the bottom. So the top fiber you will have compression and the bottom fiber you have tension. So the top fiber the stresses should be, after deducting the losses, that is loss factor into P by A minus P into E into Y by I plus dead load moment into Y by I plus here it's the time of working, there is live load moment also, ML into Y by I must be less than or equal to the allowable stress in compression at the time of working load. Similarly you have at the bottom fiber you have tension, so this bottom fiber's tensile stress must be less than greater than FTW, that is the tension allowable tensile stress at the time of working. That is, you can see here the FTT, FCT, FCW and FTW are the permissible stresses at transfer and working respectively for the tension and compression. So I have called this as equation 1, 2, 3, 4. You can see here I have called this equation 1, 2, 3, 4 the stresses at different stages. So now I will consider equation 1. From equation 1 I could write it as equation 1 I could write it as here this P by A, I can write it P by A minus P into E into Y by I must be greater than or equal to FTT minus MD into Y by I. At limiting state I will take it as that the extreme condition I will take it as equal to, so is P by A minus P into E into Y by I must be equal to FTT minus MD into Y by I, and substituting that value to the top fiber equation in working stress, working load, that is equation number 3, I will replace this value by substituting the value for this. So I will get from equation 1 I will get P by A minus P into E into Y by I is equal to FTT minus MD into Y by I. Substituting this value in equation number 3, put this in equation number 3, equation 3 you will get the loss factor into FTT minus MD into Y by I plus MD into Y by I minus ML into Y by I must be less than or equal to FCW. Rearranging this I will get MD into 1 minus efficiency plus ML into Y by I must be less than or equal to FCW minus eta into FTT. That is, I will get, rearranging this, I will get this value as MD into 1 minus eta plus ML divided by Y by I, that is the 1 by section modulus, that is I by Y. I could write it as the section modulus, that is here we are considering the top fiber, that is section modulus of the top fiber. If there is a non-symmetrical section, the section modulus for top fiber and bottom fiber ZT and ZB will be different, must be less than or equal to FTR. That is, FTR is a quantity that is given as FTR is equal to FCW minus eta times FTT, and there is a range of stress at the top fiber. This is the range of stress at the top fiber. That is this FTR. I can write it as FTR is equal to range of stress at the top fiber. FTR is equal to range of stress at top fiber. Now similarly, this I had taken equation number 1 and 3. Now at the bottom, if I am writing from equation 2 and 3, similarly if I am doing this from equation 2 and 3, I could get it equation 2 and 4, that is at the bottom stresses 2 and 4, I will get it like md into 1 minus eta plus ml by zb must be less than or equal to eta into fct minus ftw. This I will call it as less than or equal to FBR, where FBR is the range of stresses at the bottom, where FBR is equal to the range of stress at bottom. So once we have obtained this, substituting back the value for equation or rearranging the equation for ZT and ZB, I will get the section modulus required. That is rearranging these two equations. Suppose I am calling this equation as number 1, 2, 3, 4 is done. This is 5 and this is 6. I am calling this equation as number 5 and 6. I can rearrange this equation, rearranging this equation 5 and 6. Arranging this equation 5 and 6, I can write it as equation 5 and 6. I can write the ZT, that is the section modulus required at the top for the top stress fiber, should be greater than or equal to ml plus 1 minus eta into md divided by ftr. Similarly, the section modulus required for the bottom fiber ZB must be greater than or equal to ml plus 1 minus C into md divided by FBR, and we can use the design formula for section modulus based on this. That is, this is the design formula for section modulus of the structure required, or the beam required. That is design formula required for section modulus. Design formula required for section modulus. So your section modulus Z value should be greater than these values, such that this final stresses at the top and bottom fiber will be safe. Now you need to find the value for the pre-stressing force and the eccentricity that should be applied, such that your stresses will be under control. You have the maximum tensile stress at top fiber during the time of transfer, which means your maximum tensile stress at the top fiber you had during the time of transfer, and minimum compressive force at the bottom fiber. You should ensure that there is a minimum compressive force at the bottom fiber, and the maximum tensile stress should also be ensured. So if I am checking, the minimum pre-stressing force required will be obtained by selecting the maximum tensile pre-stress at the top fiber during the time of transfer and the minimum compressive force at the bottom fiber. That is, we should provide the pre-stressing force. I told you the pre-stressing force we will call the stress due to the pre-stressing force. We told that we'll call this as F superior, that is the top fiber we call it as F superior, F suffix SUP, and the bottom we call it as F inferior. That is, I can write P by A minus P into E into Y by I as F superior, and P by A plus P into E into Y by I as F inferior. So if I am writing here from equation 1, I can write F superior must be greater than or equal to FTT minus, here mg is your md. Okay, this is md due to gravity load, md by section modulus for the top fiber. And from equation 4, I could write F inferior must be greater than or equal to FTW by eta plus mq, this is ml plus md into efficiency divided by ZB, that is section modulus for the bottom fiber. But you have the value for F superior and F inferior from equation 1 and 2. This is from equation, not from equation 1 and 2, but you have the general equation for F superior and F inferior like this: P by A minus P into E by ZT and P by A plus P into E by ZP. After adding these two equations, you will get it like this. If superior, you will add these two, you will rearranging this equation, you will get it like this, and adding these two, you will get the value for the minimum pre-stressing force in this way, that is A into F inferior into ZB divided by plus F superior into ZT divided by ZT plus ZB. Similarly, subtracting these two equations, you will get the maximum eccentricity that you need to provide, such that the minimum pre-stressing force and the maximum eccentricity required for maintaining that stress, which is safer for the structure, will be obtained by adding these two equations and or subtracting these two equations. And this above methodology is used for computing the section modulus required, that is, this method is used for calculating the section modulus, and the minimum eccentricity and maximum eccentricity is found out using this method. So I hope you are clear with this. Read some standard textbooks, you will get more idea on this if you are not getting this, or you can ask me. Thank you.